All right, so in this video, we're going to take a look at uh, scientific measurements, and we're also going to be taking a look at some of the base units, mass, temperature, and then also taking a look at some of the derived units. So let's jump down to scientific measurements. And a measurement would be an example of a property or a characteristic that's known as a quantitative property. So something that can be measured is known as a quantitative property, and that is in contrast to or in contrast with a qualitative property, which is not measured, but it can simply just be described. So for example, something like the color of a substance would be an example of a qualitative, versus the mass of something would be quantitative. Okay, so we're going to focus here on quantitative properties called measurements. And typically when we make any measurement, we always have, every single measurement should have the quantity or the amount and the unit. Okay, that gives us an idea of how big or small that particular thing is. So for example, there are a couple different systems that you are probably familiar with. There's the English system that has units of feet or gallon pounds, quarts, ounces, etc. Whereas the metric system, which is what we're going to focus on in our class, and a derivative of the metric system called the SI system, includes units such as the meter, liter, kilogram, grams, etc. Okay, so it's not that we're not going to see the English system, but we focus a lot more heavily on the metric system in science and in chemistry in particular. So this revised metric system called the SI system, or the SI units that we're going to be using. SI here stands for the international system. And I know they're kind of reversed because the SI actually comes from the French version of this Système International, however you pronounce it. So it looks sort of backwards, but that's where it comes from. So it's used universally by scientists, and as a result, it's very easy to share information and collaborate on things. So there are 7 basic SI units, or 7 base SI units that we're going to encounter. Some of these we're going to see way more frequently than others, so we're going to highlight those, and the other ones we're really not going to touch a whole lot on. So the first one here, and you need to know these, the base unit for length is the meter, and you also need to know the symbol. For the symbol for meter is small m, lowercase m. The SI unit for mass is the kilogram, small k, small g for kilogram. The metric unit for mass is actually grams, and the amounts that we use in the lab, for example, would dictate us using those smaller units, but the SI unit here is kilogram. The unit for time is seconds, and that's abbreviated small s. Electric current we don't see a lot of until maybe, not maybe, but we'll see that in Gen Chem 2. That's the ampere, has a symbol big A. We're going to see temperature a lot. The SI unit for temperature is the Kelvin, which has the symbol big K. And then the amount of a substance, the unit there is the mole, M-O-L-E, which is abbreviated just M-O-L. Not much of an abbreviation, but we're going to see that a lot when we get deeper into the course. Luminous intensity, known as the candela, we're really not going to talk a whole lot about that. So the ones highlighted in yellow are the ones that you absolutely need to know, those base units. Now, what makes a metric system and the SI system by extension very useful and very user-friendly is the fact that we use these prefixes that we simply stick in front of the base unit, hence the term prefix. And what these prefixes do is they change the size of the unit. Okay, they make the size either bigger or smaller. And those prefixes, whenever you put them in front of the base unit, they always mean the same thing. So for example, there are several of these that are listed here in our table, and you need to know some of these. You don't need to know all of them, and this is just this is not an exhaustive list by any means, but it is a list of the common ones, and out of these, we're going to focus in on the most common out of them. So the first one that we need to know is giga. Giga has a symbol big G, and giga means 10 to the 9, right? Or a billion of something. So a gigawatts, for example, would be 10 to the 9 watts, or a billion watts. A mega is another prefix that also increases the size of the unit. Mega means a million, or 10 to the 6 of something. So a megahertz, for example, would be a million hertz. A megagram would be a million grams. A megasecond, a million seconds, etc. Kilo is the other unit that increases the size of the unit. Kilo means 1,000 or 10 to the 3. So a kilometer, 1,000 meters, kiloseconds, 1,000 seconds, etc. So these are the ones that increase the size of the unit. And the ones underneath are the ones that now decrease the size of the unit. So out of these, there's several more of the smaller prefixes, and we need to know these as well. So deci, symbol small d, means 1/10 of something. So deciliter is 1/10 of a liter. A decigram, 1/10 of a gram. Centi, 1/100th of something, or 10 to the -2 of something. So a centimeter, 1/100th of a meter. Milli means 1,000th of something. So a millimeter would mean 1/1000th of a meter. Micro, which has this unusual looking symbol. That's the symbol, it's pronounced mu is the name of that symbol. So it looks like a U with a tail at the front. And that means 1/1,000,000th of something. So a micrometer would mean 1/1,000,000th, or 10 to the -6 of a meter. Now, micro anything is 1/1,000,000th of that thing. Nano is the next one. Nano means 1/1,000,000,000th of something. So a nanosecond is 1/1,000,000,000th of a second. And then pico is the last one. We don't see pico as frequently, but we do see it occasionally, especially when we get down to maybe sizes of atoms. Even so, we really don't get down to that scale. It's usually nano that we see. So the green ones here are the ones that decrease the size of the unit. You need to know these. Okay, the metric system is very, very important in chemistry and in science in general. So let's just take a look at a couple of these. We're not going to go into a whole lot of detail, just to give you a sort of a flavor of them. So mass, for instance, is a measure of the amount of matter in an object or a sample. And we defined mass back when we defined chemistry in one of the earlier lectures. And the amount of matter in something does not change. So the mass of a pen, for example, is going to remain constant regardless of where that pen is. Okay, the amount of matter in it is not going to, well, maybe the amount of ink changes. Let's use a different example. Let's say a cup, for example. Okay, assuming the cup is empty. The mass of the cup is not going to change. Now that's different. Mass is different than another term that is sometimes used interchangeably with it, which is weight. And weight is not the same as mass. Weight actually is a measure of the gravitational force in an object, and that depends on gravity. And obviously, gravity varies from location to location, so the weight actually can change. So for example, something has a weight here on Earth, and the weight is going to be different on the moon, for instance, where the gravity is less. Whereas the mass of that same object is going to be a particular mass on Earth is going to be the same mass on the moon because the amount of matter in it is constant. We saw before the SI unit, base unit for mass is a kilogram, kg, small k, small g, but in chemistry, we use a little bit smaller unit, which is a gram more frequently. When it comes to the sizes of atoms and the masses of atoms and these really, really tiny things, even subatomic particles, for instance, we use an even smaller unit called the atomic mass unit, or AMU. And 1 AMU is a very, very tiny fraction of a gram. So 1.6 times 10 to the negative 24 is about the size of an AMU. And we use that a lot when it comes to looking at atoms, molecules, and subatomic particles as well. Jump over to temperature. So there are a couple different scales that we use of temperature that we use in chemistry. Degrees Celsius is used a lot, and the reference points there are the freezing point and the boiling point of water, which are 0 degrees and 100 degrees Celsius respectively. The other scale that we use is the Kelvin scale. And the Kelvin scale is also known as the absolute scale, or sometimes we refer to it as the thermodynamic temperature. And the relationship between the Kelvin scale and the Celsius scale is fairly straightforward. We just simply add 273.15 to the Celsius temperature in order to get to the Kelvin temperature. And on the Kelvin scale, we establish the lowest possible temperature, which is 0 Kelvin, and that's known as absolute 0. So going back and forth between Celsius and Kelvin, a fairly straightforward calculation that we can do. If we want to go in the opposite direction, if you want to go from Kelvin to Celsius, for instance, then if we rearrange our equation, we can see that degrees Celsius would be equal to the Kelvin temperature minus 273.15. So those are the two that we're going to use a lot more frequently in chemistry. The other temperature scale that you're probably more familiar with is the Fahrenheit scale. And as reference points there, the freezing point of water is 32. This should be Fahrenheit. And 212 degrees Fahrenheit would be the freezing point and boiling point of water respectively, because they correspond to the same range in the Celsius scale from 0 to 100, but between 212 and 32, there's actually 180 degrees in this range. But in the Celsius scale, between the same reference points, there are 100 degrees. When we go from Celsius to Kelvin, or Celsius to Fahrenheit, Fahrenheit to Celsius, we need to take this relationship into account. So whenever you see the formula that relates Celsius to Fahrenheit, you always have this 9/5 or 5/9 relationship. That actually comes from the differences in the degrees between those two reference points, right? So between the boiling point and freezing point of water on the Celsius Fahrenheit scale, we have 180 degrees. On the Celsius scale, we have 100 degrees. If we simplify this, we end up with 9/5. Okay. And that's where that actually comes from. It's not something that we make up. It actually comes from the relationship. All right, so if you want to go from Celsius to Fahrenheit, we simply take the 9/5, we multiply it by the degrees Celsius, and then we add 32 to it. The 32 is to account for that difference in the reference point for the freezing point being 0 degrees Celsius on the Celsius scale to 32 degrees Fahrenheit on the Fahrenheit scale. So in addition to the units that we talked about before, mass, units of mass, volume, etc., there are derived units that we are going to use, that we're going to encounter. And we can derive these units from some of the SI base units, or from other units. And a good example of this would be, for instance, units for volume. So for example, if I have a small cube, let's say the cube has dimensions like this. Let's say the sides of this cube here is 1 centimeter. And as you probably know, all the different edges of the cube are the same. So the volume then of this cube would be 1 centimeter times 1 centimeter times 1 centimeter, which is the same as 1 cubic centimeter. right? Or 1 cc, cubic centimeter. And that, if you were to fill that with a liquid, that would occupy a volume 1 milliliter. Small m meaning milli, and big L for the liter. So the equivalence there is 1 cubic centimeter is equal to 1 mil. And the cubic centimeter here being your derived unit. It's derived from the other units that we talked about previously. Another very common example of a derived unit is density. And density is simply the ratio of a substance's mass to the volume. So typically density, the density equation, D equals M over V, where M here is equal to the mass and V is equal to the volume. So if we substitute, for instance, units for mass and volume in here, we can end up with another derived unit. So for example, if I have grams as my mass and liters as my volume, I end up with grams per liter as my unit, my derived unit for density. A thing to note about this specific example, but you'll see other examples like these. Sometimes you'll see units like these being represented this way. So you have grams times liters to the -1, right? Remember, we saw this notation before, right? L liter to the -1 is 1 over liter. This means the same as grams times 1 over liter, which is the same as grams over liter. Okay, so don't get confused if you see this type of notation. It's just a different way to represent the same relationship, the same derived unit that we have before. All right, so using that density relationship, that density equation, we can then go ahead and try to solve some problems. And as I mentioned in a couple of the earlier videos, the first week or two of chemistry really is just establishing most of your math basis. You really can't do chemistry without knowing a little bit of math, and we'll take a look at an application of that here. So let's say we have the following example. We see ice cubes float in a glass of water because solid water is less dense than liquid water. And it says calculate the density of ice given that at 0 degrees Celsius, a cube that is 2 centimeters on each side has a mass of 7.36 grams. And then B, determine the volume occupied by 23 grams of ice at 0 degrees Celsius. So let's focus in, first of all, the first part of this problem, part A. And whenever you have a problem to solve, whether it's something, as simple as this, or whether it's something a little bit more, maybe there are several more steps involved, or maybe these may look slightly more challenging. It's always a good step to try to organize the information first. Okay, so let's organize what we're given. The way that we're going to organize is list. What are we provided with? Okay, what are we given? What do we need to find? What we need to calculate, in this case. And then hopefully by identifying what we're given, what we need, we can then figure out what we're going to use to get there. Okay, so in this problem, we are told we want to calculate the density of ice, right? So we want to calculate density. So how do we calculate density? Well, we just talked about it. Density is equal to the mass over the volume of that particular substance. So what are we given in the problem? Well, we're given the mass of this thing as 7.36 grams. And then are we given the volume? Well, we're told that we have a cube. But for that cube, we were told that the each side has a length of 2 centimeters. 2.0 centimeters. Okay, so that's what we're given. The mass of this cube of ice. We're given the dimensions of this cube of ice. We need to calculate the density. And because we need to calculate the density, we're going to use the D equals M over V. So in order to do this, we need to calculate the density. We need the mass, which we're given. So we can simply substitute that here. Now we also need the volume. Well, we're not given the volume explicitly, but we're told that we have a cube. And the dimensions of the cube here, we have 2 centimeters times 2 centimeters times 2 centimeters, right? The length of the edge of each side of the cube is the same. So the volume then of the cube, just like we did in the example before, would be 2 centimeters times 2 centimeters times 2. Okay, so this would be 2 times 2 times 2. That'll be 8.0. It's 2.0, sorry. Cubic centimeters. So we didn't just cube the actual value, but we also cubed the unit as well. So we have 8.0 cubic centimeter as the volume. We can now go ahead and substitute this into our equation. So we have D equals the mass 7.36 grams divided by the volume 8.0 cubic centimeters. And we end up with 0.92 grams per cubic centimeter. Or sometimes you can represent this as 0.92 grams times centimeters to the -3, right? Remember, that's the same way to express that derived unit of volume. I'm sorry, of density. So if I calculate my density as 0.92 grams per cubic centimeter, I can then go ahead and solve part B, where it's asking me now to determine the volume occupied by 23 grams of ice at 0 degrees Celsius. So for part B, what we need to determine here, we need to calculate the, what do we need to find? Determine the volume. And what are we given? Well, we're given the density because we just found it. And that density was 0.92 gram per cubic centimeter. And then we're also told that we have the mass being equal to 23 grams of that ice. Okay, so what we're going to use, that density equation, D equals M over V. Okay, now I need to calculate volume. I need to take this equation, I need to rearrange and solve for the volume. So there are a couple ways that you can do this, right? So using this equation, D equals M over V, you can get to the answer a couple different ways. Show you one way. So we can, for instance, cross multiply. So we have D over 1 is equal to M over V. We cross multiply, V times D here equals V times D. And that's equal to M times 1, which is M. Now divide each side by D to get rid of the D. And I end up with volume equals mass over density. Okay, so that's one way to solve it. Then we can go ahead and substitute our values in. The values that were given or that we calculated previously. So the mass there was 23 grams. And that's divided by 0.92 grams per cubic centimeter. Okay, so that's the same as saying 23 grams times 1 cubic centimeter over 0.92 grams. Okay, so the grams are going to cancel. We end up dividing 23 by 0.92, and we end up with 25 cubic centimeters as the volume. Right, you notice here that the grams cancel away. The only unit I'm left with is the unit of volume, cubic centimeters. So the answer makes sense, both in terms of the number, but also in terms of the unit. So we should be able to take a simple equation like this, rearrange it, solve for any of the unknowns.